Hello students, myself Ms.Sonali Patil, Assistant Professor, Department of Mathematics, Kokli College, Kolhapur. This is our second lecture on the topic normal subgroup and its properties from Algebra second paper number 8 from B.Sc second year. Okay, so let's start with the next point, results related to normal subgroups. Okay, so see here one theorem. The intersection of any two normal subgroups of a group is also a normal subgroup, and this is very important theorem. Okay, so let starts with the proof. Let G be a group and H and K be normal subgroup of G. To prove that H intersection K is also a normal subgroup of G. Okay, so since E belongs to H and E belongs to K, therefore E belongs to H intersection K. Okay, now hence H intersection K is a non-empty subset of G. Let G belongs to G and H belongs to H intersection K, then H belongs to H intersection K implies that H belongs to H and H belongs to K. So since H and K are normal subgroup of G, so therefore G inverse belongs to H for all G belongs to G and H belongs to H, and G inverse belongs to K for all G belongs to G and H belongs to K. So this implies that G inverse belongs to H intersection K for all G belongs to G and H belongs to H intersection K. Hence, H intersection K is a normal subgroup of G. Okay. Now see here one definition. Let H and K be two subgroups of a group G. We define HK is equal to in the set HK such that H belongs to H and K belongs to K. Note that HK is a non-empty subset of G. Okay. Now see next theorem. HK is a subgroup of G if and only if HK is equal to KH. Okay, so let's start with the proof. Let H and K be two subgroups of a group G. Let HK be a subgroup of G. To prove that HK is equal to KH. Okay, so let X belongs to HK, then since HK be a subgroup of G and X inverse belongs to HK, so this implies that X inverse is equal to HK for some H belongs to H and K belongs to K. So this implies that X is equal to HK inverse is equal to K inverse H inverse belongs to KH. Okay, so therefore X belongs to HK, this implies that X belongs to KH. So this implies that HK is a subset of KH, and this gives equation number 1. Again let Y belongs to KH, then Y is equal to KH for K belongs to K and H belongs to H. So this implies that Y inverse is equal to H inverse K inverse belongs to HK. So this implies that Y belongs to HK. So thus KH is a subset of HK. This gives equation number 2, and hence from equation 1 and 2 we get HK is equal to KH, and conversely let HK is equal to KH to show that HK is a subgroup of G. So let AB belongs to HK. Now AB belongs to HK. This implies that A is equal to H1 K1 and B is equal to H2 K2. For some H1 H2 belongs to H and K1 K2 belongs to K, then AB inverse is equal to H1 K1 into H2 K2 inverse is equal to H1 K1 into K2 inverse H2 inverse is equal to H1 into bracket K1 K2 inverse into H2 inverse. Now K1 K2 inverse into H2 inverse belongs to KH is equal to HK. Thus K1 K2 inverse into H2 inverse is equal to HK for some H belongs to H and K belongs to K. Then AB inverse is equal to H1 into HK is equal to H1H into K belongs to HK. Thus AB inverse belongs to HK for all AB belongs to HK. Hence HK is a subgroup of G because it satisfies our inverse property. Okay, now see next theorem. If H is a normal subgroup of a group G and K is any subgroup of group G, then HK is equal to KH. So let's start with the proof. Let G be a group, let H be a normal subgroup of G, and K be any subgroup of G. To prove that HK is equal to KH, let HK belongs to HK, where H belongs to H and K belongs to K. We can write HK is equal to KK inverse HK is equal to K into K inverse HK. But H is a normal subgroup of G, therefore H belongs to H and K belongs to G. This implies that K inverse HK belongs to H. This implies that HK is equal to K into K inverse HK belongs to KH. So hence HK is a subset of KH. This gives equation number 1. Again, let KH belongs to KH, where K belongs to K and H belongs to H. We can write KH is equal to KH K inverse K is equal to KH K inverse of K, but H is a normal subgroup of G, so therefore H belongs to H and K belongs to G. This implies that KH K inverse belongs to H, so this implies that KH is equal to K inverse HK into K belongs to HK, and hence KH is a subset of HK. This gives equation number 2. Hence from 1 and 2 we get HK is equal to KH. Okay, now next theorem. If N is a normal subgroup of G and H is any subgroup of G, then NH is a subgroup of G. Okay, so let's start with the proof. Let G be a group and H be a subgroup of G. Let N be a normal subgroup of G. Since N is a normal subgroup of G and H is any subgroup of G, therefore by theorem number 6 we must have NH is equal to HN, and now N and H are subgroup of G such that NH is equal to HN. Therefore by theorem number 5 NH is also a subgroup of G. Okay, now see next theorem. The product of any two normal subgroups of a group is a normal subgroup of the group. Okay, so let's start with the proof. Let G be a group, let H and K be a normal subgroup of G. To prove that HK is a normal subgroup of G, as K is a normal subgroup of G, K is a subgroup of G. Since H is a normal subgroup of G and K is any subgroup of G, therefore we must have HK is equal to KH. And now H and K are two subgroup of G such that HK is equal to KH. Therefore HK is also a subgroup of G. Now to show that HK is a normal subgroup of G, let G be any element of G and HK be any element of HK. Then H belongs to H and K belongs to K, and we have GHK G inverse is equal to GH G inverse into GK G inverse belongs to HK, because H and K are normal. Hence HK is a normal subgroup of G. Okay, now next theorem. Let H be a subgroup and K be a normal subgroup of the group G, then H intersection K is a normal in H. Okay, so let's start with the proof. Let G be a group, let H be a subgroup of G and K be normal subgroup of G. Since H and K are subgroup of G and H intersection K is a subset of H, so therefore H intersection K is a subgroup of H. To prove that H intersection K is a normal subgroup of H, let G belongs to H and H belongs to H intersection K. Hence, since H is a subgroup of G, therefore G belongs to H and H belongs to H. This implies that GH G inverse belongs to H. Also G belongs to H. This implies that G belongs to G and H belongs to K. Since K is normal in G, therefore GH G inverse belongs to K. Hence GH G inverse belongs to H intersection K for all G belongs to H and for all H belongs to H intersection K. So hence H intersection K is normal subgroup of H. Okay, now see here next point, center of group. So definition of center of group. Let G be a group and let Z of G is equal to set of X belongs to G such that xg is equal to gx for all g belongs to g, then z of g is called the center of group G. Okay, now see here one theorem. The center Z of G of a group G is a normal subgroup of G. So let's start with the proof. Let G be a group. We have Z of G is equal to set of x belongs to G such that xg is equal to gx for all G belongs to G. To prove Z of G is a normal subgroup of group G, first we shall prove that Z of G is a subgroup of G. So let x1 x2 belongs to Z of G, then x1 G is equal to gx1 and x2 G is equal to gx2 for all G belongs to G, and we have x2 G is equal to gx2 for all G belongs to G. So this implies that x2 inverse of x2 G and x2 inverse is equal to x2 inverse into gx2 x2 inverse. So this implies that gx2 inverse is equal to x2 inverse G for all G belongs to G, and this implies that x2 inverse belongs to Z of G. Now x1 x2 inverse of G is equal to x1 of x2 inverse G is equal to x1 into G x2 inverse is equal to x1 G x2 inverse. So is equal to G x1 x2 inverse is equal to G x1 x2 inverse. So therefore x1 x2 inverse belongs to Z of G for all x1 x2 belongs to Z of G. Hence Z of G is a subgroup of G. Now we shall prove that Z of G is a normal subgroup of G. Let G belongs to G and X belongs to Z of G. Then Gx G inverse is equal to Gx G inverse is equal to Xg G inverse is equal to X belongs to Z of G. So thus G belongs to G and X belongs to Z of G. This implies that Gx G inverse belongs to Z of G, and hence Z of G is a normal subgroup of group G. Okay, so thank you for listening. We cover the next point in next lecture. Thank you.